There. So in the video that I had you guys watch over differentiating natural logs on that one e-learning day, we talked about the derivative of natural log. And just a real quick refresher, if I had a function like 3x plus 5, let's say natural log of 3x plus 5, and I wanted to find the derivative of this function. Remember, the derivative rule is u prime over u. It's the derivative of the argument over the argument. So the derivative of this would be 3, because that's the derivative of the inside, over 3x plus 5. Okay, so that's our derivative rule for natural logs. Today is all about natural log integration. Now, if you notice all the problems we're going to be doing, the examples, none of them have natural logs in them. The rule that we're going to be using when we integrate, we're going to be ending up with natural log functions. Kind of like going backwards. Like if I had this and I wanted to go backwards, we would end up with a natural log function. Similar idea. Okay, so again, recall the derivative of natural log of x is 1 over x. That's the derivative using that rule from the e-learning video. Provided that x is greater than 0, because you can never take the natural log of a negative. So x is going to have to be a positive number. Okay. Well, let's think about this in the reverse order. All right. What if I had 1 over x and I wanted to integrate this? So I'm going to rewrite this right here. And let's say I wanted to go ahead and integrate both sides. Now, first of all, remember when we talked about our power rule a couple weeks ago, I said we can use our power rule provided we don't end up with this situation. This is undefined by the power rule because this is x to the negative first. And when you increase that by 1, you get 0. And when you divide by 0, everything blows up. So you can't use your power rule for 1 over x. But look what happens here. The integral and the derivative are going to undo each other, right? Those are just going to undo each other. And then we get the integral of 1 over x equals. Now here's our rule, and there's one little wrinkle to this. It's not just going to be the natural log of x. It's going to be the natural log of absolute value of x plus c. We still can't forget about plus c when we're doing indefinite integration. But the reason the absolute value is going to be necessary is because the argument has to be positive. Like I said up here, you can't take the natural log of a negative number, so we're going to have to be using absolute value. So here's our rule. The integral of 1 over x equals the natural log of the absolute value of x plus c. Now this is also going to work. We're going to have a lot of u substitution going on. Remember, if we differentiate the natural log of u with respect to x, we get u prime over u for u greater than 0. And we're going to kind of do the same exact thing that I did up here. I'm going to integrate u prime over u. So I have u prime over u equals the derivative of natural log of u. And I'm going to integrate both sides. And in doing so, the integral and the derivative cancel. And I get the integral of u prime over u equals natural log of the absolute value of u. And remember, u is just some expression of x. Like it could be 6x plus 1 or something like that. U is standing for an expression for x. So absolute value of u plus c. But the bottom line of me showing you this is this right here is rarely going to happen, especially on the AP test, but even on questions in here, rarely are you going to be integrating 1 over x. You're usually going to be integrating some fraction, and we're going to have to be using u substitution to get it in the form of 1 over u. To use this rule, we have to get everything to be 1 over x or 1 over u. That's kind of our goal. We have to make our fraction look like this to use natural logs. Okay, so now we are just going to practice, but we do have a lot of u substitution coming up. So if I want to integrate 1 over 6x plus 1 with respect to x, the the most common wrong thing students do, so don't write this, but a lot of students will look at this and say, oh, natural log, absolute value of 6x plus 1 plus c. And then you're immediately wrong. So it's not always just going to be natural log of this denominator. We do have to go through our u substitution to make sure we get to the right answer, okay? More times than not, you're going to be setting your denominator equal to u. So I'm going to have 6x plus 1 equal u. And remember, you want to choose something for u where the derivative or some form of the derivative shows up elsewhere. The derivative of 6x plus 1 is 6. 6 is a form, it's a constant, so it's a form of 1. We'll be able to pull it out. So I'm going to have u equal 6x plus 1. So du equals 6 dx. So now I have 1 over u, that's going to be u, and then dx, I have to replace dx, remember, so divide by 6. And now I can do my replacement. I can write this as 1/6 from right here, the integral of 1 over u du. So now I have it in that form. So now I'm going to go ahead and write this as 1/6 times the natural log of the absolute value of u plus c. And now I just take the u expression, 6x plus 1, plug it in for u, and I get 1/6 natural log absolute value of 6x plus 1 plus c. So notice the other way, we didn't end up with that 1/6 out in front. So go ahead and pause the video, and I want you guys to try example 2. See if you can do u substitution on example 2, and then play it after you try it. Sorry, my son was in here with me and had to go to the bathroom. Okay, let's do this. So I'm going to have u be, actually I'll just put the answer up since you've already tried it with the work. Here's the work you should have. So I had u be the denominator. And notice that the derivative is 3x squared, which is some form of the numerator. In fact, it's the exact same. How nice is that? Holy moly. So 3x squared plus 1. Which is exactly what we have to replace. 3x squared plus 1 dx, all of this becomes our du. I don't like to write du over u. You'll see a lot of stuff in the book or handouts will say du over u. For me, it just makes more sense to write 1 over u du. I don't know why. But then we get natural log of absolute value of u plus c, and then we just make our replacement. Put x cubed plus x back in. Bada bing, bada boom. All right. Let's look at example, yeah, we could do 3. 3 is a pretty quick one. So we're going to integrate this. We do still need to keep in mind our trig derivative rules, things like that. We should know that the derivative of tangent is secant squared, just things that we have to, have in the back of our mind always, which means I can have u be tangent of x. So du equals secant squared x dx, which is exactly the numerator part. So that's all du. So I can write this as 1 over u du, which is then the natural log of absolute value of u plus c, and then put tangent back in. All right, the next one. So it's easy when we get into, this goes for all math. It's easy once you get into a habit of doing something a certain way. You get on autopilot. You're doing the homework and you start doing the problems all the same. Think about the u substitution homework you had the other night. I threw some in there that weren't u substitution just to make sure they're not always going to be like that. And I bring that up for example 4. If we're just trucking along, and every single time we've set the denominator equal to u, we come to this, you're like, well, u equals x squared plus 1. And then you get stuck because the derivative of x squared plus 1 is 2x. And you have an x squared up here. So you're stuck. You can't have u be the denominator. This, I can't say it has shown up a lot on the AP test, but they've told us to make sure that we teach it. And so I always do, just in case. But anytime your powers are the same, or the top one is bigger, okay, so it's kind of something you have to be on the lookout for. If your degrees are the same or the top is bigger, we actually have to perform long division before we can continue on the problem. And they told us that long division is possible to be on the AP test. I haven't seen it, but I do want to make sure I cover my bases. So as soon as you notice your degrees are the same or the top is bigger, we are going to divide the top fraction by the bottom fraction. So off to the side, I'm going to perform a long division. It's been a while since we've done this. I know it showed up once first semester. I don't like how I wrote that, but hopefully you guys can see that. So I like to account for missing terms. So notice I'm dividing by x squared plus 1. So I put a 0x in the middle there. I would do that for any missing terms in the numerator too. So to refresh your memories of long division, we take the first term divided by the first term. So x squared divided by x squared is 1. And I line up my term, so I put it above the constant. Then I multiply this back through, so I get x squared plus 0x plus 1. And then I'm going to subtract downward. So I'm going to subtract all these. I like to flip all the signs and then add. So I get x here. These cancel. And then when you did this in Algebra 2, you would repeat the process, right? You would take what you get and divide again. But as soon as this degree is less than the leading degree here, you're done. This is your remainder. And then here's how we write the remainder. So when we divide, we get 1, and then it's plus, and then it's remainder over divisor. So x over x squared plus 1. And you're sitting there thinking, man, that is not fun. But sometimes it is a necessity. And here's why. So that means that this thing here, the integrand, is the same as this. It's the same exact thing as that. Which means now, instead of integrating this, we can integrate this whole thing. So we have the integral of 1 plus x over x squared plus 1 dx. And when you're integrating separate terms that are being added or subtracted, you could split it up into separate terms. So we can have the integral of 1 with respect to x plus the integral of x over x squared plus 1 with respect to x. And now we're going to go ahead and integrate each of these separately. So the integral of 1 with respect to x is x. This, though, the integral of x over x squared plus 1, the reason this is in this section is because now we have a u substitution candidate. I don't know how to integrate this, but I notice if I have my denominator be u, the derivative is 2x, and I have an x up here. So this I'm going to integrate through u substitution. So u equals x squared plus 1. Du equals 2x dx. I'm trying to replace x dx, so divide by 2. So this integral becomes 1/2 the integral of 1 over u du, which is 1/2 natural log absolute value. And I'm fine if at this point you just put the x expression back in. That's absolutely fine. So absolute value of x squared plus 1. Which means our final answer, when I put these together, this was x, plus this one became 1/2 natural log x squared plus 1, and then plus c. Sorry. Now notice, and this happens a lot, and it'll happen on the answer keys when you check the solutions, notice the absolute values became parentheses. For no rhyme or reason, they became parentheses. There is a reason, though. So the whole reason the absolute value needs to be there is to keep the argument positive. But think about x squared plus 1. No matter what you plug in for x, this is always going to be a positive expression. So whenever possible to get rid of absolute value, get rid of them and put parentheses. Most students hate looking at absolute value anyway because a lot of our algebra rules don't apply. So put parentheses when you can. Fun one. All right. We'll do a couple more. We're not going to do all these on the notes here, but we'll do a few more. So the next one says, solve the differential equation knowing that y goes through 0, 4. So they're giving you an initial condition, and they're giving you a differential equation. And so think about when we did slope fields and we found particular solutions. Think about what step 1 always was. Separate the variables, separate the variables, separate the variables. We have a separable differential equation. So we are going to move the dx over. So dy equals 2x over x squared plus 9 dx. Next step, integrate both sides. We're trying to go backwards to find y. That's what we're after. So we get y on the left side equals. And then over here, we have to integrate, and notice we have a u substitution candidate. We're going to have u be the denominator. Du equals 2x dx. Oh, look how convenient that is. So we're going to have 1 over u, and then this whole top here is du. So 1 over u du, which means it's just going to be the natural log, because we're just integrating 1 over u, so it's going to be the natural log of absolute value of u, which is x squared plus 9. Plus c. I skipped a few steps there. Probably not the best teaching I've ever done, but hopefully you can follow what I did there and why I was able to skip a few steps. I wouldn't suggest it. But now I have this initial condition 0, 4, and I need to find c. So I'm going to plug in my initial condition and find my c value. So I'm going to put 4 where the y is. And then I put 0 where the x is, so natural log of 9. The absolute value can go away at that point because 9 is positive, so I don't need the absolute value. And I'm trying to find what c is, so subtract natural log of 9. So c equals 4 minus natural log of 9. Which means my final answer, I go back to my y equation, my final answer, y equals natural log of x squared plus 9. I don't need the absolute value because x squared plus 9 is always going to be positive. And then plus 4 minus natural log of 9. But the big thing is going back to the beginning, separating the variables, and then integrating both sides. And there we are. All right. Definite integrals, same idea. We're going to be doing the same thing with definite integrals. We're going to do u substitution, replacing the x limits of integration with u limits. In fact, I bet you could even pause and try number 9, but I'm just going to go through, and this will probably be our last one right here. Actually, no, we'll do number 11. So I need to integrate, and at first glance, I don't have a strategy, except I notice if u is x squared plus 1, du is 2x, x shows up on top. How convenient. U equals x squared plus 1. Du equals 2x dx. I'm trying to replace x dx, so 1/2 du equals x dx. So now I'm going to have 1/2, don't forget that 1/2 here. When I first started doing these, especially just U sub in general, when I started teaching, I would always forget about this, the 1/2. I'd forget to put it out in front. And then we would have 1 over u du. I didn't put limits on there because I'm going to change them. I'm just going to keep everything in terms of u from here on out. So when x is 0, u is 1. And when x is 3, 9 plus 1, the upper limit will be 10. And I'm just going to keep I'm never going to put the x squared plus 1 back in at this point. You could, but I'm just not. So I'm going to have 1/2. And then this is going to be the natural log of the absolute value of u from 1 to 10. Remember, we're using the fundamental theorem of calculus, so we have to integrate first. Some students make a mistake of plugging 10 into right here and 1 into right here, but you have to integrate first. And now plug the 10 in and plug the 1 in. So 1/2 natural log of 10 minus natural log of 1. And then going back to our log properties, anytime you have a log of 1, regardless of the base, this is 0. Because this is really saying e to what power gives you 1, and this is 0. So it goes away. So we really just have 1/2 times natural log of 10. Which is one way they might write the answer. They might put the 1/2 up as a power. Remember a log property, you could put the 1/2 as a power. And they might write it like this. I mean, this might be the correct answer choice here with multiple choice. You just, especially with logs, you just have to know the manipulations. Because you might do all the calculus correct and then get to the end and not see your choice, and you might just be missing a manipulation. You might get here and say, ah, crap, my answer's not there, when it's this one right here. All right, last one. So we haven't really talked about integrating some of these trig functions. Like there's no rule for integral of tangent to have memorized. We know the derivative of tangent, but we don't know the integral. But the reason that it's in this section is because, say this does come up, I do want you to have kind of an ace up your sleeve. I want you to have a way to be able to get to the answer, because the rule for this is really gross. So I'd rather you have a strategy to do this if it does show up. So think about how we can rewrite tangent as a fraction. This whole lesson has been about fractions. And so tangent we can write as sine over cosine. And now we can go through and do our u substitution, because the derivative of cosine is negative sine, which shows up here. So we're going to be able to get to the answer through u substitution. So I'm going to have u equal cosine of x. So du equals negative sine of x dx. Hey Garrett, are you listening to all this? Are you learning calculus over here? No?
Is the video still going?
Yeah, it's still going. Yeah. Maybe in like 10 years you'll remember this and it will have sunk in. Okay, so I need to move the negative over.
No, I'm not learning anything.
You're not learning anything?
No.
Well, maybe the people watching this video aren't either. I never know. Okay, so sine of x dx is du. I'm going to have a negative on the outside. 1 over u du. Which gets me to negative natural log of absolute value of u plus c. And then I put the cosine back in. So here's my point. You can either have this rule memorized, that the integral of tangent of x is negative natural log absolute value of cosine of x plus c, or if this by some miracle shows up on the AP test, write it as a fraction and do u substitution and get to the answer. I've never seen this show up, but it is fair game. I mean, it's part of the standards. There's our answer. All right, best of luck to you all, and hope you all have a wonderful day.